This is Guillermo Babylonia. Today I'll be presenting my project on predicting 24-hour ICU mortality using the Mimic4 database. The problem. In intensive care units, early identification of high-risk patients is critical for timely intervention. We're focusing on the first 24 hours of ICU admission, a critical window where mortality risk is highest. Our goal is to build a machine learning model that can predict which patients are at risk of dying within their first 24 hours in the ICU. Why this matters? Early warning systems can help clinicians allocate resources more effectively. Can trigger additional monitoring or interventions for high-risk patients. Potentially save lives through earlier, more targeted care. Let me walk you through our data sources. Mimic4 database. This is a freely accessible critical care database from Beth Israel Deaconess Medical Center. Contains de-identified health data from over 300,000 ICU patients. For this project, we're using 4 key tables. Patients table, demographics, age, gender. Admissions table, hospital admission details and mortality outcomes. ICU stays table, ICU-specific information including length of stay. Chart events and lab events, clinical measurements, vital signs and laboratory results. Our filtered dataset. We filtered for patients with ICU stays of 1 day or less, giving us the first 24 hours. This resulted in approximately 19,000 patient records. Mortality rate in this cohort is around 12%, showing significant class imbalance we'll need to address. Let me briefly walk through the code organization. It's designed for clarity and modularity. The notebook follows a function-based architecture with 8 main sections. Section 1, Import libraries and setup. All necessary imports with proper configuration. Sets plotting styles and warnings. Section 2, Data loading function. Loads patients, admissions, ICU stays tables. Returns structured data frames with record counts. Section 3, Cohort definition function. Merges tables and filters for 24-hour ICU stays. Creates age groups, young, middle, senior, elderly. Displays comprehensive cohort statistics. Section 4, Clinical data loading function. Chunked loading of chart/lab events. Filters for specific vital signs, HR, R, SBP, SpO2, temp, and labs, CREAT, K, Na, Gluck, WBC. Saves processed data for faster future runs. Section 5, Feature engineering function. Complete feature pipeline. Aggregates measurements, imputes missing values, removes outliers. Creates derived risk indicators, is_elderly, HR_abnormal, SBP_low, SpO2_low. Section 6, Analysis and modeling function. Full training pipeline. 70 to 30 train test split with stratification. Returns trained model and all evaluation metrics. Section 7, Visualization. Creates 3 key visualizations. Feature importance, prediction distribution, ROC curve. Section 8, Results summary function. Results_summary, function, comprehensive metrics and clinical insights. Confusion matrix breakdown, performance metrics, risk factor analysis. Execution pipeline function. Main block at bottom calls all functions in sequence. Clean, reproducible, and easy to understand. Each function has clear purpose and returns specific outputs. Data processing pipeline. The Mimic4 database is massive, with hundreds of millions of rows. Here's how we handled the data. 1. Efficient data loading. We read the data in chunks of 10,000 rows to avoid memory issues, filtering each chunk as we go. 2. Feature selection. We selected the most clinically relevant features, 5 vital signs, heart rate, respiratory rate, systolic blood pressure, oxygen saturation, temperature, and 5 lab tests, creatinine, potassium, sodium, glucose, white blood cell count. 3. Feature engineering. We took average values for each patient and created new indicators, such as an elderly flag for patients 65 or older, and binary flags for abnormal vital signs. For data cleaning, we handled missing values with median imputation and removed physiologically impossible outliers, ensuring data quality. Model development. For prediction, we chose a random forest classifier. Why? It captures complex, nonlinear relationships, works well with both numeric and categorical data, resists overfitting, and provides feature importance scores. We used 200 decision trees, with a maximum depth of 15 to balance complexity and generalization. Class weights were balanced to handle our 88% survival versus 12% mortality split. Stratified 70 to 30 train test split and cross-validation helped validate our model. In total, 18 features were used after encoding, all clinically interpretable. Results and model performance. Now, the results. Our model achieved an AUCROC score of 0.92, indicating strong ability to distinguish between survivors and non-survivors. Mortality precision was 0.83, and recall was 0.53. The top predictors were low oxygen saturation, high white blood cell count, elevated creatinine and glucose, and low systolic blood pressure. Elderly patients and those with abnormal vital signs were at much higher risk, aligning with established medical knowledge. Limitations, future work and conclusion. No model is perfect. Let me address limitations and future directions. Current limitations. 1. Class imbalance. Despite balancing techniques, we have far more survivors than deaths. 2. Temporal information. We use average values, missing time series trends. 3. Limited features, only 5 vital signs and 5 lab tests. 4. Single center data, mimic 4 is from one hospital, may not generalize. Future improvements. 1. Time series analysis, use LSTM or recurrent neural networks to capture trends. 2. More clinical data, add medications, procedures, diagnosis codes. 3. External validation, test on data from other hospitals. 4. Calibration, fine-tune probability thresholds for clinical deployment. 5. Explainability, add SHAP values for individual patient predictions. Conclusion. We successfully built a mortality prediction model that processes massive healthcare data efficiently, achieves 98% AUCROC in identifying high-risk patients, provides clinically interpretable features, runs on standard hardware in under 10 minutes, could serve as an early warning system in ICU settings. This demonstrates the power of machine learning in healthcare, transforming raw clinical data into actionable insights that could help save lives. Thank you.